This is video on doubly reinforced beam and we are using ultimate load method of design. Now see, the problem is in ultimate load the depth of neutral axis is restricted. That is, it is maximum, it can be half that of effective depth. Now what happens if you require more capacity? Then what you do is you provide some compression steel AC as shown in left side figure. Now what will be the advantage? That you will get capacity, moment capacity due to concrete also, and this additional capacity due to this compression steel. So this is what is explained in this side. Look at the term which has come up, mu term, and look at the first part. This 1/4 BD square sigma Cu means what? The maximum ultimate moment the beam can take. And what is the second term? It is the moment which can be given by the compression steel which you are putting. So look at the second term very carefully. AC is area of compression steel multiplied by sigma SCY minus 2/3 sigma C. You see, this is the stress term. Actually, sigma SCY is the allowable stress in compression steel. And minus 2/3 sigma Cu is why, because that much concrete is taken out when you put the steel. And multiply by D minus DC. You know what is D minus DC? It is difference. It is the distance between the top steel AC and bottom steel, that is at the length or at the depth of effective depth it is put. Okay, now that see, in addition to your balance steel you will need this extra steel, and that will give you the couple extra couple, and it will increase the moment capacity. So you, as usual, two equations. The second equation is total tension is total compression, and the first equation is the moment capacity. So a second equation, left hand side, you see AS sigma Cy. What is AS? Total steel at the bottom, and sigma Sy is the yield strength. Now sigma Cy we have called it. Okay, and on the right hand side of the second term, it is you see the first term is the moment capacity, maximum moment capacity, where x is equal to 0.5 d we are used, and second term is AC into the stress. So same thing is there, C is equal to T, this will give you neutral axis, and then you use the first equation to find moment capacity. This can be best demonstrated by the problems, by the numericals, and there will be again only two type of questions. One is the design, and second is analysis. This time we are going to do design problem first. So read this. It says design reinforced concrete beam of size 45 centimeter effective depth by 25 centimeter width to fail at ultimate load of 4,000 kg centimeter. Assume depth to the compression steel is 5 centimeter and to the tension steel is 45 centimeter. Take sigma SY 2800, sigma SCY 2500, and sigma CU as 300. Now see, you don't know whether you have to design as doubly reinforced or not. So first you do any given problem, you find out 1/4 BD square into sigma CU. And you find, see, that is the maximum moment this beam can take. So this has come out to 3796875, which is less than 4,000. So additional moment is this, which is 4,000 minus 379,875, and that for this additional moment we need compression steel. So see, how do I find compression steel? I am just equating this moment to understand the in the second term or second line, which has now come in. Look at the right hand side. 40 is what? 40 is the distance between the two steels. 45 minus 5. 2500 minus 300 into 2/3 is the effective stress there. 2500 is allowable steel stress and minus that concrete part of it. This multiplied by ASC. Okay, so what you have done is area stress into that 40 gives the additional moment, and from this you can work out your ASC. Now at the bottom there are two parts. One is corresponding to the mu by bd square, I mean 1/4 bd square sigma cu, that is 379,685 multiplied by 2800 is the allowable stress, 81 I'll call it that part. Then and 45 minus 22.5 by 2 is like, because here see the effective I mean the neutral axis depth will be half the d. So from this you can work out 81, and corresponding to ASC, see, to balance out this 203125 you need 82. That I equate to 40 into 2800 and 82. So I have 81, 82, and the total design is 40.12 plus 1.812, that is 41.99. And here, XU maximum is 22.5. That's how this 22.5 has come here. So this is how we have found the steel, that is we have designed. How much is the steel? At top 2.21 and at the bottom 41.99. And how 41.99 has come? It is 81 plus 82. Now let's look at analysis problem. Very simple. Here is a beam with all the details of it. Sigma Cu, sigma S1, sigma SCy are same. Sigma Sy is the allowable yield stress at the bottom, tension steel, and sigma SCy is allowable tension yield stress at the compression steel. Both are same here. Total area of tension steel is 16, area of compression is 2, B is 20, effective depth 35. This 1.86 centimeters square is a mistake, just ignore it, and depth of compression steel is 5. Now look at, now all you have to do is write proper expression. See, from this, that is C is equal to T, I can get a neutral axis depth 9.9. Mind you, no one has told you, you are just told to find capacity with additional steel. No one has told you that it is really double reinforced beam. It is just you have put some compression steel and found out. So from this I'll get 81 at the bottom, which is 1.86, and now 81 at the bottom. 1 minute. 81 at the bottom. How did we get it? 2600 into 2 upon 24, 2800. How did we get that? Because see, AC is 2 and corresponding 81 I have found 1.86. And then here you put in mu the two components. First is 2/3 sigma Cu B into X. X is 9.91, D minus X by 2. That's the first part. And second is due to that ASC. ASC sigma SY minus 2/3 sigma Cu. D minus DC is the distance between the two steels. And you get total capacity as 1.35 into 10 raised to 6 kg cms, and that is unit is kg cm. Okay, so this was problem on the finding moment capacity. I would call it analysis. Previous was on the design, and that's all about doubly reinforced beams. So in examination we will have at the most 4 type of problems: analysis design singly reinforced, analysis design doubly reinforced. Thank you.